Hello, welcome to Chapter 7. Only 2 chapters left to go. Chapter 7, Chapter 8, and we will be finished with differential equations. And so what we're going to talk about in this chapter is basically the Laplace transform. How we can change, pretty much we're just taking the equation and we want to change the variables. And we're going to transform the way the actual equation works. So differentiation and integration are transforms. Since these operations transform a function into another function. So when we integrate, when we differentiate, we're transforming one function into another function. And that's what we're going to do here. The Laplace transform is just another transformation. So we're going to consider the improper integral, the integral of, and here we have the integral of two variables. We have a function of two variables times a function of one variable, and it's taken to infinity. And this is basically what we're going to do. This is the Laplace transform, where we're going to take two functions, one of two variables, one of another. And since this is taken with respect to t, we're going to be treating the s in that k equation as the we're going to treat s as a constant. And so here we have the function k of st is called the kernel of the transform, because this is what we're going to use to transform the function. We're going to be able to get rid of our t's and put everything in terms of s's. So here we have our kernel, which in this case, for this section and our next sections, is going to be e to negative st. So our kernel is this exponential raised to the negative st. The integral is called the Laplace transform. So the definition for let f be a function defined for t greater than or equal to 0, then the integral is going to be represented as such. So this is when our t is always positive. We have our Laplace transform, where we have this L representing, okay, we're taking a Laplace transform of this function f of t. And then we're just going to put it into the integral, where we're going to have e to negative st, that's our k of st, times our function, whatever's inside of our Laplace, and taking it with respect to t. And then we're going to work on this integral, and we're going to be able to transform the way that our function f of t looks. Alright, so it said this, again, our integral has to converge in order for this to be the case. So now, we will use a lowercase letter to denote the function being transformed, and the corresponding capital letter to denote its Laplace transform, for example. So if I have the Laplace of f of t, and I have a function f of t, the Laplace transform is shown by capital F and then of s, because we're changing variables from t to s as well. Alright, so if we take a lowercase g, our transform will be cap g, lowercase y, cap y, all of those of s. So let's go ahead and do with an easy example. Example 1, we're going to find the Laplace transform of just 1. So our function is 1. So the Laplace transform of 1 is equal to, I'm going to put it into my integral. So here's my kernel. So the integral from 0 to infinity times e to negative st times 1 d of t. And because I'm taking an integral from 0 to infinity, I'm just going to say, hey, the limit as a approaches infinity. That way I don't have the infinity. Now, it doesn't matter. The rest of these, I'm just going to keep infinity. That way I don't have to keep writing the limit as a approaches to infinity. So I didn't have to say from 0 to a. I could have said from 0 to infinity. But if you're going to change it, it's best to show why you changed it. All right, of e to negative st d of t. Again, that 1 is just, kind of go away. So then we go ahead and take the integral of that. If we take the integral of e to negative st, we get negative 1 over s e to negative st. And we're going from 0 to a as a approaches infinity. Now, here is the note. S has to be greater than 0 in order for this to work, in order for this to converge. If s is less than 0, then our exponent is going to be positive. Then I have an exponential going off to positive infinity. It's not going to converge. So s has to be greater than 0 in order for this to work. So here we go. We plug in our a, we plug in our 0. When I plug in a, I get negative 1 over s e to negative sa plus 1 over s e to the 0. this is equal to, as a approaches infinity, this function, e to negative sa, is approaching 0. So this, as we approach infinity, this is 0. So all this is just 0. And then e to the 0 is just 1, so it's just plus 1 over s. The reason why it's plus is because there was a negative there. It would have been 2 negatives. So that's why it's plus. And so we just get 1 over s, and there is our Laplace transform. So f of s. All right. Example 2, we're just going to do the same thing, but here we actually have t as our function. And so we're going to do a Laplace transform of just t. So we denote as such, and we're going to plug it into our integral, 0 to infinity, e to negative st times our function, in this case t. Now in order to do this, I'm going to have to do integration by parts. I look at u. Looks like, again, I say I late. I forget what y'all have used for this, but I like to use my algebra before I do my exponentials. And so u is going to be t. Then that means that my dv is going to be e to negative st dt. Now the derivative of t is dt, and the integral of e to negative st is negative 1 over s e to negative st. And so I have my u v's, the u dv's, and I'm going to plug them in. So u times v, so I get negative t over s e to negative st. And now I'm going to go ahead and find that from 0 to infinity, because this is integrated, plus 1 over s. I'm going to pull this 1 over s out. It's plus because that's a minus sign, so that's plus 1 over s. And then I'm just going to keep this inside, e to negative st, and then I'm going to take that dt and stick it right there. And so now we're going to integrate this. Now, as I work on integrating this, I notice that if I take this from 0, the integral from 0 to infinity, if I plug in infinity in for my t's, this is going to become 0. So that's why I get 0 there. And then when I plug in 0, that t is 0, so 0. So 0 plus 0 is 0. So all of this is just 0. Plus, and then now I'm going to integrate this. So negative 1 over s e to negative st. Plug in my infinity, plug in my 0. E to negative s times infinity, that's going to converge to 0. Plus 1 over s e to the 0, that's just going to be 1 over s. So 1 over s times 1 over s is equal to 1 over s squared.